solubility product. Now, it's called Ksp, but I like to call it KS Sleepy because it's really one of those things where not much happens. It's all about partially or like almost insoluble solids in aqueous solution and the dynamic equilibrium between the precipitate and the ions in solution. Okay, so we're just going to start this off with just a few refreshers here. Solubility, that's the amount of substance that can dissolve at a given temperature. Okay, so there's a max amount. Once you hit that solubility level, any other salt you add just sinks to the bottom. Okay, so insolubility changes with temperature. Okay, so now here's what happens. When we have a solid that's slightly soluble, those are the ones that when we were using our solubility chart in the fall, we would have said are insoluble. Okay, but actually what happens is they're so slightly soluble. They give you a dynamic equilibrium and some of those ions go into solution. And it's enough to make a whole little section about it in our book on solubility product. So the ions dissolve, and then some of the ions reprecipitate, and it sets up an equilibrium system, okay? And so all these same equilibrium rules apply. So capital K, equilibrium constant, Ksp, Sp means solubility product, okay? That's just an equilibrium constant. So all the equilibrium rules will apply. Okay, so here's our system. Calcium fluoride solid yields reversibly, calcium with a +2 F minus. So our Ksp expression is just our equilibrium expression. We have products over reactants. And remember that we don't put solids in the equilibrium expression. Okay, so there's nothing in the denominator for this Ksp expression because the products are the soluble ions and the reactant is a pure substance, the solid. Okay, so it kind of simplifies the system a little bit, the calculations. Okay, that just kind of reemphasizes what I just said. The Ksp expression, with every equilibrium problem, you want to write the equilibrium expression first. And so this is what it looks like for a solubility product system. Okay. So some things that we can do to make things dissolved faster, like stirring or grinding to increase the surface area, those will increase how quickly a substance dissolves, but it doesn't change the maximum amount that can dissolve. Okay, so that will help it get to its solubility limit faster, but those things don't actually change the amount that can dissolve. Okay, one other thing here is that Ksp is an equilibrium constant for the system, whereas solubility talks about how much of that solid can dissolve. So we have two separate terms that we're dealing with here. Ksp, which is our solubility product, equilibrium constant. Solubility, which is moles per liter that can dissolve at a certain temperature. Okay, we're going to go through these. I'm going to show you how to do these sample problems. So here's our first problem from the notes. All right, we have copper 1 bromide. It has a measured solubility of 2.0 times 10 to the negative 4 at 25 degrees Celsius. So we want to calculate Ksp. So I'm just going to highlight the important information. So we know the solubility of the substance, and we want to figure out Ksp. So first thing I'm going to do is I'm going to make my ice chart. These are really good ice chart problems. Okay, so here's our chemical reaction. So copper 1 bromide forms copper with a +1 plus bromine with a -1. Okay, and the way this works is our initial conditions, we have only the solid and no ions. So we have 0 and 0 for the concentration of the two ions. And then when it sets up its equilibrium, it's going to go up by x, and this one's going to go up by x because they both have coefficients of 1. So at equilibrium, we have 2 x's. Okay, so far so good. Now, I'm going to write my Ksp expression. Always start with your equilibrium expression. Cu plus and Br minus. And raised to the power of the coefficient, they're all 1s, so that's all we got to do. Now, there's a very important tip that I'm going to tell you. X is equal to the solubility. So that makes this problem really easy because if you notice here, we know the solubility. It says the solubility in the problem. And when we do our ice chart, this value of X that we get is our solubility. So now all we got to do here is plug in what we know into our ice chart and solve for X. So we are told this, no, we want to solve for Ksp. All right, so Ksp is going to be equal to x squared because we're going to plug in x for each of the 2 ions at our equilibrium conditions, okay? And then we know that x is equal to the solubility. So all we got to do is put the solubility in and solve for solve for Ksp. So we have 2 times 10 to the negative 4 squared. So our Ksp value is going to be 4.0 times 10 to the negative 8. Okay, do you notice what I'm seeing here? Our Ksp value is really small. It's really small, 10 to the negative 8. These systems tend to be very reactant favored, okay? The Ksps tend to be extremely small. It doesn't ask that in the question, but I just figured I'd point it out. Okay, let's go on to the next one. Here, again, we have a problem where we want to calculate Ksp. We know the solubility, and we know the compound. So what we have to do first is make our ice chart. So we have bismuth sulfide, and that's a solid, yields reversibly. Now we have 2 Bi, because remember the subscript becomes the coefficient, and those are plus 3s. And we have 3 S's. Okay, so initial conditions, 0 and 0. Now we're going to do plus 2x, because it's going to go up by x times the coefficient, and plus 3x. So at equilibrium, what we get is 2x and 3x. Okay, now we got to write our Ksp expression. So Ksp is equal to Bi raised to the power of the coefficient. So that's squared, and the sulfide ion cubed. Okay, and what we're going to do here is we know the solubility, so what we have to do is to figure out the concentration of the Bi, we have to multiply 2 times the solubility. Because remember, X is the solubility of the compound. All right, so what I'm going to do is my Bi is going to be, here, I'll just do this over here on the side. So the Bi concentration at equilibrium is going to be 2 times the solubility, 1.0 times 10 to the negative 15. Okay, so that's going to be 2 times 10 to the negative 15. Okay, my sulfide concentration is going to be 3 times x, and we know x is the solubility, so it's 3 times 1.0 times 10 to the negative 15. So we get 3.0 times 10 to the negative 15. All right, so far so good. So what we're going to do is plug these 2 things into our equilibrium expression to solve for Ksp. And don't forget that you have your exponents there. So we have 2.0 times 10 to the negative 15 squared times 3.0 times 10 to the negative 15 cubed. Oh my gosh, the answer is ridiculously small. 1.1 times 10 to the negative 73. What? Yes. Yep, it's that small. So it's basically insoluble, okay? It's so incredibly slightly soluble that it lays far, far, far to the left. Okay, one more here. This time we know the Ksp, okay? And we want to calculate solubility. So this time we are looking for X, because remember, X is the solubility. All right, so we got to start with an ice chart. We have copper iodate, CuIO32. It's copper 2, so it's got a +2 charge. Iodate, there's 2 of them, and that's a -1. 0 and 0 are the initial conditions, plus X and plus 2X. So in equilibrium problems, the coefficients get double duty. So here we have Ksp. Here's our equilibrium expression. You always have to write that. Can't skip that step. IO3 squared. What did I do here? 2x, there it is. So I'm going to plug in to my Ksp expression X for the copper and 2X for the iodate. Now, one of the most common mistakes with these problems is forgetting to square the 2 and the X, okay? So we have X, and then we have 2X squared. All right, we're almost home. I can plug in my Ksp value, which was given in the problem, 1.4 times 10 to the -7. And algebraically, this is going to be, oops, see what I just did? I almost did it myself. 4x cubed. Okay, when we do the math, we get x is equal to 3.3 times 10 to the -3 moles per liter. Okay, so that tells us the solubility. That is the maximum amount of solute that can dissolve per liter. The next thing is to talk about relative solubility of different compounds. All right, so remember, we're talking about compounds that we would normally consider to be insoluble or extremely slightly soluble. Okay, so we can't just compare the value of the Ksp equilibrium constant and say that a substance is more soluble because it has a bigger Ksp or a smaller Ksp, whatever. We have to think about what kind of ionic compound it is. Okay, so there's 2 possibilities. The first possibility is pretty straightforward. If you're comparing, it's basically like comparing apples to apples versus apples to oranges. Okay, if you're comparing apples to apples, what that means when you're talking about ionic compounds is that you have ionic compounds that produce the same number of ions. Okay, so those compounds, you can just look at their Ksp values and put them right in order. The largest Ksp value versus the smallest. The largest one would have the largest solubility. Okay. Now we have to be a little careful when we have compounds that have the different numbers of ions. In that case, it requires a little more extra work. Okay. So here's an example of the first case. These are all 1-to-1 ions. So if you look at the chemical formulas, we have 1-to-1 cation to anion. We have silver iodide, copper 1 iodide, and calcium sulfate. And remember that calcium sulfate is 1-to-1 ion, even though it has a polyatomic ion. It still has 1 calcium ion and 1 sulfate ion. So in this case, we can look at the Ksps and we can say with confidence that calcium sulfate is the most soluble, then copper iodide, and then last is silver iodide. Okay, so if you have a situation like this, it makes the problem very easy. Now, when it gets complicated is when you have something like this where it's not all the same number of ions. So copper sulfate is actually a 1-to-1 compound, 1 copper to 1 sulfur, copper 2 sulfide. Silver sulfide, however, has 2 silver ions for every 1 sulfur ion. So it's a 2-to-1. So it produces 3 ions total. And bismuth sulfide is 2-to-3. So it has 2 cations and 3 anions. So in this case, we can't say just by looking at the Ksp which is most soluble. What we have to do here is we got to figure out the value of our X, our solubility, which is X, using, the ice chart like I showed you in the previous problems. Okay, so in this case, and I'm going to show you a little trick with this, okay? So I've got to go over to my good notes to show you this. Okay, so here's where we left off. Hey, what are you doing? Okay, there we go. Okay, so in this first case, these are all 1-to-1 cation to anion, so we can compare them directly. We already talked about that. Now, in our second case, we can't compare them directly. All right, so what I wanted to show you was, okay, CUS. All right, so when we do our equilibrium expression, we get Cu plus 2 plus S with a minus 2, okay? Our Ksp is going to be equal to Cu plus 2 times S with a minus 2. Okay, when we do our ice chart and everything, this comes out to be X squared, all right? Because it's a 1-to-1 ratio. We get X and X, so Ksp is equal to X squared. Now, this one is Ag2S. We get 2Ag plus S, 2 minus. Ksp is going to be equal to Ag squared times S to the minus 2. All right, what we end up here is 2x squared times x. So in this case, we get 4x cubed, okay? So we have a 1-to-1. Here we have a 2-to-1. So for whenever it's a 1-to-1, we get it, Ksp is x squared. If it's 2-to-1, we have Ksp is 4x cubed. All right, if it's 3-to-1, like sodium Na3P, we're going to get 3Na plus P minus 3. Our Ksp is going to be Na plus cubed and P to the minus 3. So what we get for this one is 3x cubed times x, which gives us 27x to the 4th. Okay, so if you have a 3-to-1, and then the last one, which I'm going to put up to the top here, is like we have with the bismuth. If you have Bi2S3, yields reversibly 2Bi with a plus 3, and 3S minus 2, our Ksp value is going to be the Bi ion squared and the S ion cubed, which translates to 2x squared times 3x cubed. So we get, oh my gosh, why can't I do this math in my head? We get 4 times 27x to the 5th, which is equal to 128, I think, x to the 5th. Okay, so this is a regular pattern, okay? So here we have a 2-to-3 ion. So 1-to-1 ions, Ksp is going to be x squared. And remember, x is your solubility. 2-to-1 ions, and it's 1-to-2 or 2-to-1. It works out either way. Ksp is 4x cubed. Okay, 3-to-1, Ksp is 27x to the fourth. Okay, and then last but not least is our 2 to 3. Ksp is 128x to the fifth, which seems like a lot. But anyway, I just thought I would show you how mathematically that works out. So when we're talking here about the solubility here, the way this solubility is calculated was to take the square root of it. For since this is for, I'm sorry, where am I going here? For copper sulfide, okay, the Ksp is equal to x squared. For this one, the Ksp is equal to, this is a 2 to 1 ion, is equal to 4x cubed. Oh, that's the solubility, sorry. I'm getting ahead of myself. All right. The Ksp here is 4x cubed. So that's where they get the x from down here. For this one, it's Ksp is equal to 128x to the fifth. All right, so when you're trying to compare solubilities of different kinds of salts, and they don't have the same number of ions, you've got to go through this process to figure out the value of x for each one from the solubility product. All right, that's all I want to say about that. The next thing on our list is the common ion effect. We've done some problems similar to this before. All right, so we're just going to go right into the example here. So the common ion effect is when you add an ion into the system. And we know from Le Chatelier's principle that you add something to an equilibrium, it's going to shift to the other side. Okay, so now in this example, we're going to work through pure water, and then we're going to try it with a common ion. All right, so here's what we've got. We want to consider the solubility of silver chromate when it's dissolved in 0.1 molar compared to dissolved in pure water. Okay, so let's just think about the solubility in pure water first. So what we need to do first is we're going to make our ice chart, of course. So we have Ag2CrO4, that's our solid, yields reversibly, 2Ag plus CrO4 minus 2. I'm going to write my Ksp expression. Let's go ahead and get that out of the way. Silver raised to the second power times the chromate ion to the first power. Okay, 0 and 0 are the initial in pure water. The change, plus 2x and plus x. Okay, so at equilibrium, we have 2x and we have x. Okay, so remember that x equals solubility. So if we solve for x, we're solving for the solubility in these problems. Okay, so let's plug in what we know. 9.0 times 10 to the negative 12 is our Ksp. And we have 2x for Ag, so 2x squared times x. Notice that it's a 1 to 2 ratio. So Ksp is equal to 4x cubed. I just showed you how to derive that before. It's okay if you don't memorize that because it's easy enough to work out. Cubed. Okay. So when we solve for x, when we do the math, we get 1.3 times 10 to the negative 4 moles per liter. Okay, so that's the solubilities. That's how much we can dissolve of this compound in pure water. Now, we're going to do the same thing, but this time we're going to dissolve it in a solution of silver nitrate. So in this case, what's happening here, we have our same equilibrium system as before. Okay, so we have Ag to CrO4. So I'm going to still make the same ice chart I made before, 2Ag plus CrO4 minus 2. Now, the difference here is our initial conditions. The common ion in this case is the silver, okay? Because notice that silver nitrate has the silver ions in it. So silver nitrate is what that really means is it's a solution that has already 0.1 molar of silver in it. So our initial concentration of silver is going to be 0.100. Instead of starting with 0, like we did in the pure water, we're starting with 0.1 molar of silver. Okay, now just thinking about Le Chatelier's principle, if we're starting with silver, it's going to force the equilibrium to the left. Okay, so we're expecting this to have a lower solubility. Okay, let's see if that's the case. All right, so plus 2x. Oh, I changed colors. And plus x. Okay, so at equilibrium, it's 0.100 plus 2x and x. Now, the amount that it dissociates is very, very, very small. So we can say this is approximately equal to 0.100. All right. So now when we plug this into our Ksp expression that we had from before, we've got 0.1 squared times x. Oh, I forgot to put in the Ksp value. The Ksp value is still the same. 9.0 times 10 to the negative 12 is equal to 0.1 squared times x. Okay, and so what we're going to do here is we just solve it mathematically, and x is equal to 9.0 times 10 to the negative 10 moles per liter. Okay, now, just like we were expecting, the solubility goes down in a common ion. So the solubility started here at 1.3 times 10 to the negative 4 moles per liter. Still not very much, but when you add that common ion, it forces the equilibrium to the left, so our solubility goes down. So there's less ions dissolved in solution. All right, try the next one. Okay, I'm going to show you how to do this one. Calculate the solubility of calcium fluoride in a 0.2 molar sodium fluoride solution. So it's important to recognize this as a common ion, because here's the thing. This is where people get really confused because they're not sure what's what here. Now, this one, we are given the Ksp. So the one that has the equilibrium constant is the one that the compound that is in the equilibrium system. All right, so the CaF2 is the solid that's in our ice chart. That's not K, that's Ca. I don't know if I said K. Okay, so we have, all right. Now, this solution of sodium fluoride is introducing F as our common ion. Sodium is a spectator ion, and this solution is, sodium fluoride is completely soluble, okay? Whereas CaF2 is very slightly soluble. Okay, so in our ice chart, that means we're starting with 0.025 molar of the sodium fluoride and 0 of the calcium. All right, so we have plus x, we have plus 2x. Okay, so then we get x, and we get 0.025 plus 2x. And again, this is so small that we can approximate it to be 0.025. Because look at how tiny our equilibrium expression is. I mean, our Ksp value is times 10 to the negative 11. So it's so small that that change is negligible. Okay, so here's our Ksp expression. Ca plus 2 times F minus squared. Now we can plug in what we know. X goes in for the calcium ion, and 0.025 goes in for the fluorine ion, and it is squared. All right. And oopsies, we know the Ksp. I did that last time too. Where are we? Ksp is 4.0 times 10 to the negative 11. All right, so we do the math. We solve for x. X is our solubility, 6.4 times 10 to the negative 8 moles per liter. Okay. There we go. That's it. All right, one last bit. This is a really long section. Okay, so the last thing we want to address here is pH and solubility. So pH can really affect the solubility of a salt. And we talked about this a little bit when we talked about when you dissolve salts and if you get acids or bases, solutions. So like if you dissolve ammonium chloride, the ammonium ion acts as a weak acid. So you have a slightly acidic solution, okay? So when we talk about these Ksp systems, sometimes there's ions that can affect the pH. Now, the most obvious ones is something like this, like magnesium hydroxide, for example. This is one of the equilibrium systems we studied when we did our Le Chatelier's lab. This is the one with milk of magnesia. Okay, so milk of magnesia contains magnesium hydroxide, and magnesium hydroxide ions are very slightly soluble. So in solution, you get this dynamic equilibrium between the solid, magnesium hydroxide, and the magnesium and the hydroxide ions. And a hydroxide ion, it will change the pH. It's going to make it a base. As a matter of fact, OH is a strong base, okay? Now, what we did in the lab is we squirted hydrochloric acid in there. When you put the hydrochloric acid in there, it selectively removes the hydroxide ions. So you're pulling out the hydroxide ions because you're reacting it with the acid, and it causes the equilibrium to shift to make more ions. So by removing the OH, you can push the equilibrium to dissolve more of the magnesium hydroxide. Okay? So you have to just take into consideration the ions that are being produced in the equilibrium. And if there's a hydroxide ion, that is a huge red flag that there's going to be a question about pH. Because hydroxide ions are a strong base. And we know from our pH unit that if you can figure out the pOH, you can figure out the pH. Okay? So a similar thing can happen here if you have the conjugate acid or conjugate base of a weak acid or weak base, okay? So in this case, we have the conjugate base of a weak acid. We have PO4, the phosphate ion, PO4 minus 3. So when that is dissolved in solution, that PO4 ion will act as a weak base. And so it's going to cause the pH of the system to shift. Okay? So these are things to take into consideration when you're dealing with these solubility, these Ksp problems. Because those two ions that are in solution, you just have to be aware and think about, like, okay, is this ion... Now, it only comes up in situations where it specifically says, is it an acid or a base? So then you have to think about it. If it's a common ion problem, like we did just before, typically that's going to be a totally different ballpark. So here's when you're looking at things and trying to understand if it's going to be acidic or basic solution because of the ions that are produced. Okay. That's just as clear as mud, isn't it? Okay, so you just have to... I know, that's a lot. So when these I feel like are a little more subtle because you have the PO4 3 minus ion. It's going to react with acid to form the HPO4 with a minus 2. Okay. I think that's it for this section. Nope, there's a little more. Now, this silver chloride, it doesn't have any characteristics that would affect pH because silver is got a +1. So we know that if it has a +2 or a +3, then that's going to affect the pH because it's going to act as a weak acid. We know that the chlorine ion is the conjugate base of a strong acid, so it doesn't change the pH either. So in this case, the pH is the solubility has nothing to do with pH. It's a neutral solution. Okay, that brings us to the end of section 16.1. Phew. That was an awful lot of